Let's get started. So first, again, a reminder, the final is going to be next week. As you can see, there's no block that corresponds to Monday, Tuesday, Thursday, Friday at 8 a.m. So we're going to be, the official final exam time for us is going to be Friday morning, 8 to 10:30. Okay, so that's the time that, again, I will have officially the Zoom room open. Try to take the exam during that time if you can, so that if you run into any troubles, I'll be available to help you right away. So just a reminder. So any questions on the final next Friday? Okay. I will switch back to, all right, and then what is, so it's 8 in the morning. 8 in the morning. Okay, so today we're picking up where we left off with the last class. Okay, we're going to pick up right where we left off. No slot. What do you mean no slot? It's Friday at 8 a.m. Friday 8 to 10:30. I said that you can take it anytime during the day, but officially, if you want help from me, take it between 8 and 10:30. Another question, do we have class Monday? Monday's a reading day. No, we're not having class. Use that day to study. And yeah, I would study. Do what you want. You can also catch up on old homeworks or anything like that, but I would study for the final of that day. Okay, but no, we're not meeting on Monday. Any other questions before we get started? Okay, let us begin. So today we're talking about numerical integration one more time, and then we'll dig into the final review a little bit, okay? So there will be a quiz today after class. It was the quiz that got postponed on Tuesday, so it's going to have a question on numerical integration using rectangles, a question using trapezoids, and a question using Simpson's rule, which we're going to learn today. Trapezoid rule was on Tuesday. Okay, so let's just dive right into what is Simpson's rule. So before we actually show the general Simpson's rule, we need to show the following. If p of x is just a general quadratic function, ax squared plus bx plus c, a and b and c are all just real numbers, okay? Then the integral from little a to little b of that quadratic function, p of x, is just the length of the interval divided by 6 times p at a, little a, plus 4 times p at little a plus little b divided by 2, which is halfway between a and b, and then plus little p at little b. Okay? So this is something that we can just prove directly, right? We know how to integrate this thing. Okay, so we're just going to integrate that from a to b and see what we get, and it's going to end up being this. Okay, so let's actually do this integration. The integral from a to b of, well, p of x is capital A x squared plus capital B x plus capital C dx. Okay. So just like always, let's break this up. This is the integral of the sum of a bunch of things. So let's break it up into the sum of integrals. This is equal to the integral of ax squared dx plus, or from a to b, sorry, plus the integral from a to b of dx plus the integral from a to b of c with respect to x. Okay. Well, again, we can pull this a out in front, pull this b out in front, pull this c out in front. And so when we do that, we're going to be left with, well, now, what's the integral of x squared with respect to x? Good. I'm going to get a times x cubed over 3. And we're going to evaluate all of these at a and b. So I'm going to wait a second to actually write that in. Good. Plus, what's the integral of x with respect to x? X squared over 2. Good. So I'm going to get b times x squared over 2. And then plus c times the integral of, this is really 1 dx, right? What's the integral of 1 with respect to x? Careful, that's the derivative of 1, but I want to go the other way. X, very good. I get cx at x equals b, x equals a, and then we're going to subtract. Let's see. Okay, so I plug in x equals b, and then I plug in x equals a, and I take a difference. Well, let's do that. I'm going to get, this is, oops, sorry. This is a, give myself a little more room. This is a times b cubed over 3 plus capital B times b squared over 2 plus capital C times b. There's when I plug in x equals b, right? Then I will say, well, I want to take that minus when I plug in x equals a. So I get capital A times little a cubed over 3 plus capital B times little a squared over 2 plus capital C times little a. So the rest of this problem now, showing that this is equal to this, well, we've taken the integral. We have found the left-hand side, right? The rest of this is just algebra, getting this to actually look like what's on the right-hand side here. And so a first step in doing that is going to be to redistribute. Everything here is in terms of p. P is that ax squared plus bx plus c. So I'm going to try and collect terms that have the capital A. I'm going to get those together, and then I'm going to collect terms that have the capital B. I'm going to get those terms together, and the same way with capital C, right? So when I do that, I'm going to get, well, I'm going to get a, what was a on the a? We had a b cubed over 3 minus an a cubed over 3, right? So I'm going to get a times b cubed minus a cubed over 3. Okay, everybody see that? That's what's going to be attached to the capital A. Okay, we'll do the same thing with capital B. With capital B, I'm going to have a b squared over 2 times capital B minus an a squared over 2. So that means when I do my simplification, I'm going to get plus b times b squared minus a squared over 2. That's my term with a b. Okay. And then last, the term with the C, well, that's just going to be CB minus CA. So plus C times B minus A. Now, what do all these terms, what does it look like they might all have in common? Yeah, they're all going to have a B minus A in common, it turns out, once you factor some stuff. Okay, so this is equal to A times B cubed minus A cubed. Well, you can factor that as B minus A times B squared plus AB plus A squared. And that's still over 3. Okay. If you don't believe me, well, you can just distribute what I wrote down to check, right? You can actually do this multiplication, distribute everything out, and you'll find that you'll get B cubed minus A cubed when you actually do that. Okay. B plus capital B times, what is B squared minus A squared? What does that factor into? We definitely are going to, we want a B minus A. What's the other factor? B plus A, very good. B plus A over 2. And then last, we still have plus C times B minus A. Okay, so now we've actually written everything out so that it has a factor of B minus A. So I'm going to pull that factor of B minus A out in front. Okay, and when we do, we get, this is equal to B minus A times, well, here I'm left with A divided by 3 times B squared plus AB plus A squared. That's what's left from that first term. From the second term, I'm left with B over 2 times B plus A. And then from the last term, I'm left with plus C. Okay. Grab. So that I don't keep pressing the buttons. Okay, and then from here, really, I'm going to not skip several steps, but the last thing we want to do, we have this B minus A out in front. The last thing I want to do is I want divided by 6 out in front. So I'm just going to pull out a 1/6. Okay, and so when I do that, B minus A divided by 6. Well, what am I left with? When I pull out a 1/6 from A over 3, I'm left with actually 2 times A from that first term, right? If I divide the first term by 6, I need to multiply by 6 to not change anything. And so that's where I'm getting 2A when you pull out a 1/6. Okay, so I'm going to get 2A times B squared plus AB plus A squared. What am I left with from this term when I pull out a 1/6? I'm going to be left with plus what? (3b). Very good. Exactly right. I'm going to be left with 3b when I pull out a 1/6. So I'm going to be left with 3b times little b plus little a. And then plus, well, when I pull out a 1/6 from this piece right here, I'm going to be left with 6c, right? Questions on that so far? Okay, so the last step, we have that B minus A over 6 out in front like we want. So now I just want to rewrite this so that it looks like P of A plus 4 times P of A plus B over 2 plus P of B. Well, I know how to write P of A. Let's write let's see if we can pick out a P of A from this. P of A is just capital A times little a squared plus capital B times little b plus capital C. So can we pull that out from here? And the answer is pretty easily, yes, we can. Add page. Let me copy and paste this. Copy. All right. Paste. So this is equal to B minus A over 6 times. Well, I want to have a capital A times little a squared. Well, I can use one of these capital 2A's, right, times this little a squared. Or if I just distribute everything, that's another way to think of this. So I'll distribute everything first. So this is capital 2A times B squared plus capital 2, or sorry, 2 times capital A times little ab plus 2 times capital A times A squared. Plus, then I'll distribute this guy here and here. This is capital, or sorry, 3 times capital B times little b plus 3 times capital B times little a, and then plus a 6c. Okay, and then the rest is just plugging in, making this look like P of A plus P, 4 times P of A plus B over 2 plus P of B. Okay, so this is B minus A over 6 times P of A is A times A squared plus capital B times little a plus capital C. Okay, so in writing this down, I've used one of these. So I have one more capital A times A squared left. I've used one of, where is it? It's in here somewhere. I've used one of these, a capital B times A, and then I've used one of these, right? So there's P of A. Next, I'm going to write down P of B, because the hardest one to see is P of little a plus little b divided by 2. Okay, so next is, I'm going to write down P of B. Again, this is P of A. Plus, well, P of B, P of little b, oops, is capital A times little b squared. So I'm using one of these here. Plus capital B times little b. So I'm using one of those. Plus capital C. So I've used 2 of these C's. Okay. This is P of B. Okay. So what's left over after I write those? Well, I've used only one of everything that I've underlined once, and then 2 of the C's, right? So what's left is a capital A times B squared plus 2A times little ab plus capital A times A squared. Plus, I only used one of the 3 times capital B little b's, right? So I have 2 of those left, plus 2b little b plus 2b little a, and then plus a 4c. That's what's left over, right? Does everybody see? Okay. All right. Well, then the last step, I can just rewrite this as, well, if I get all of my capital A's together, this is capital A times, well, what's left is A squared plus 2AB plus B squared. There's what's in front of, or what's multiplied by capital A, right? Plus, then I want to see what's in front of capital B. Well, or what's being multiplied by capital B. That's going to be 2B plus 2A and plus a 4C. right? And then this is then equal to a times a plus b squared plus b times, this is really 2b times a plus b, b plus a is a plus b, plus 4c. And then one more step, I'm going to pull this 4 out. That 4c isn't exactly what we want. I want a plus capital C at the end. So I'm going to divide everything by, or factor out a 4. Okay, so this is equal to 4 times a plus b squared divided by 4 plus b times the 2 divided by 4 is going to leave me with 1/2. So b times a plus b over 2, I'll write it there, plus a c. But notice that 4 is 2 squared, right? And so this is really, when you rewrite it, this is really a plus b all over 2 squared. Okay, and this part is 4 times p of a plus b over 2. So lots of algebra to show something that it is a pretty useful rule, but I will say that you're not going to have to do it a whole lot because if anyone's taking Calc 2, most of Calc 2 is about finding integrals exactly, not using numerical approximations. Why pull out the 1/6? Someone asked. That's a great question. It's just because that's what you have to pull out to make it work. The reason I pulled it out, when I know what I want to show here, well, I know that I want to show that there's a 1/6 out in front, and so that's why I pulled it out. The person who discovered this, Simpson probably, it was just, there was probably more work involved in discovering that 1/6. But if we know that it needs to be there, why not just pull it out and put it there? So that shows how you can integrate any quadratic function, right? Well, Simpson's rule is just using these parabolas to approximate the area under a curve instead of trapezoids or rectangles. Okay, so the general Simpson's rule, and this is on the interval from -1 to 1 now instead of just a to b, is this. And I'm not really going to derive it. If you want to, the way that we get this is just by, if we're looking at -1 to 1, if we're looking at some general function that we're trying to find the area of, well, you break it up into sets of 3 points, and then you approximate this with a parabola. And then you use 3 more points, and you approximate this with a parabola, and so on and so on. You use that result we just showed on each of these sets of 3 points, and you add up those areas. That's where this rule comes from. But the general rule looks like, it looks very similar to the trapezoidal rule, but there's 2 key differences. One, well, actually 3 key differences. One, n here, for the trapezoidal rule, you just needed n to be bigger than 0, right? We need at least 2 points, but if we have 2 points, we can use the trapezoid rule. For us, n has to be an even integer. So the n, we're using x0 through xn. That means that we really have to use an odd number of points, right? Because 0 through n gives me an odd number, n plus 1. But the final subscript has to be an even integer to be able to use this. That's difference number 1. Difference number 2, with the trapezoid rule, all of these coefficients were 2. But with Simpson's rule, we alternate between 4 and 2. The pattern is 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and then the last one comes after the last 4 is 1. Okay, so instead of 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, we have 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Okay, and then the other key difference is this coefficient out in front of everything. Okay. To save time, again, I'm not going to write it out because you do what I say. You just draw in parabolas, approximate the area using those, and then you find this rule. I'm more interested in, can we use this rule? Let's go, come on, there we go. So, can we use this rule to approximate the integral from -1 to 1 of the square root of 1 minus x squared with respect to x? We're going to use Simpson's rule with n equal to 6. So that means 7 x values, x0, x1, x2, x3, x4, x5, x6. Was that 7? That was 7, yes. Okay. So this is something, again, this is that same integral that I love. Hint, hint, it's going to be on the final. Maybe not exactly this integral, but something very similar, where you're finding the area of a circle. And we know this integral exactly, right? This is the area of half of the unit circle. So this is pi over 2. Okay, so we have something to compare our approximation to. Okay, so let's use Simpson's rule. We're just going to go straight into it. We're going to plug in what we know. So in this formula here, we have n is 6, right? N is 6. So we're going to have the integral from -1 to 1 of the square root of 1 minus x squared dx. This is going to be approximately equal to 2 over 3 times 6. Well, 3 times 6 is 18. Times. Well, I need to know what is x0, x1, x2, x3, and so on. Well, what are those numbers? What is x0? You find them exactly the same way as you do with the trapezoid rule. Yeah, x0 is always your left endpoint. And in general, x, what do I use? Xi is -1 plus I times delta x, where delta x is your step size between all of these equally spaced values of x. So that means x6, which we know is the last number 1, x6 is 1, but that also is equal to -1 plus 6 times delta x. So delta x, moving some stuff around, delta x is, well, I add -1, or subtract -1 from both sides, I'm going to get 2 over 6. Just like before, we have this whole interval of length 2. I'm trying to fit these really 7 points in here, but it's 6 things that I'm trying to fit into here, 6 parabolas. So I need delta x to be 2 over 6. Okay. Which is the same thing as 1/3 if you ask scientists. Okay. So in Simpson's rule, then we're going to have this is approximately equal to 2 over 18 times f of x0. Well, the only other thing I need to know is what is f of x? What function am I plugging into? Exactly. F of x is this thing. Okay, so f of -1, well, that's just 0. right? Plus, then our pattern is 4 times f of x1. So, first of all, what is x1 for us? Exactly right, negative 2/3. So I'm just going to write for now f of negative 2/3. So plus. Then next is plus 2 times f of what's our next x value? Negative 1/3. Very good. F of negative 1/3 plus, then we do plus 4 times f of, and for time, I'm going to start filling these out. But again, we're taking step sizes of 1/3 every time. So next is f of 0 plus 2 times f of 1/3. I'm out of room. Plus 4 times f of 2/3. And then plus, then at our very last step at the right endpoint, we have plus 1 times f of 1. Okay. So f of 1 is 0, so that's just going to go away. So this is, when you simplify it, 2 over 18, well, that's 1 over 9, times 0, plus 4 times the square root of, well, the square root of 1 minus 4 over 9 is 5 over 9. Okay. Plus 2 times the square root of 1 minus 1 over 9, well, that's 8 over 9. Plus 4 times the square root of 1 minus 0, well, that's just going to be times the square root of 1 is 1. Plus 2 times the square root of, well, again, 1 minus 1/3 squared, so 1 minus 1/9 is 8/9. Plus 4 times the square root of 5/9, 1 minus 2/3 squared, or 1 minus 4/9, and then plus 0. Okay. And then it's time for our calculators to shine. We're going to get 1/9 times 4 times the square root of 5 over 9 plus 2 times the square root of 8 over 9 plus 4 plus 2 times the square root of 8 over 9 plus 4 times the square root of 5 over 9. And we get 1.526. Pi over 2 is 1.57. So if you remember with the trapezoid rule, using a similar number of trapezoids, our result was a lot worse. This result is a lot closer, using only a handful of points to approximate pi over 2. So, pretty great stuff. Simpson's rule is a little more complex. You're not going to have to do it on the final. Trapezoid rule is fair game, just so you know. Simpson's rule, again, not really a fair game, in my opinion, for the final. Okay. So, are there any questions before we move on to the final review? All right. Well, do I have it on here? Or was this just me working out stuff? No, that was just me working out stuff. Okay, 1 second. Stop share. I thought I had it on my thing, but I did not. Final exam.pdf. There we go. Okay. So get back to sharing. Sharing is caring. All right, so let's look at this final exam review. So we have a number one is some sort of integral problem. You guys can help me label what type of problem all of these are. Okay, so let's start at the beginning though. This exam is going to be, again, half of it is going to be what we've covered since the last exam. So mostly integrals, integration using substitution, antiderivatives, and so on and so on. Okay. So problem one, find the integral from -2 to 0 of x plus 1 times e to the x squared plus 2x. What kind of problem is this? How are we going to approach this?
Maybe U substitution?
Exactly. U substitution is exactly right. This is a U substitution problem. Okay, so let me copy all of this, copy, and then we'll go down and give ourselves some room to work. All right, so here we go. I want to do a U substitution apparently. So what should U be? X squared plus 2x, perfect. Usually you want U to be the thing that's inside some other function. Well, that is exactly this thing, right? That's the only thing that's really inside of some other function for this example. Okay, so then if U is x squared plus 2x, then what is du? 2x plus 2, excellent. 2x plus 2, perfect. Dx, that's exactly right. So there's a couple of things you could do from here. You could either try to multiply by the right constant to get du, to get this right-hand side to look exactly like what's left over, x plus 1 dx. Or you could just try to solve for dx and plug in and hope that it works out, okay? So I'm going to, it's pretty clear to me that this is just 2 times that, right? So I'm going to divide both sides of du equals 2x plus 2 dx. I'm going to divide both sides of that by 2, okay? So I get 1/2 du, that's equal to x plus 1 dx. Okay. So then, this becomes the integral of, well, x plus 1 dx, that is 1/2 times du. And then this is e to the, well, x squared plus 2x, that is e to the u, right? And now what are the bounds now? Because this is an integral in terms of u. My original bounds, -2 to 0, were in terms of x, right? So what are the bounds on this new integral? How do I find them? I think you're thinking the right thing. We plug x into u, right? Yeah, we plug these values into u is this function of x. So I plug 0 into x squared plus 2x to find what u has to be at that top bound. Well, what do I get when I plug in 0 into x squared plus 2x? 0. Very good. And then I plug in -2. Let me do that and circle that in blue. And then that's going to give me my bottom bound, right? My lower bound. But what do I get when I plug in x equals -2? I also get 0. So Do I even need to do any work here? What's the integral from 0 to 0 of e to the u with respect to u? Zero, exactly right. This is asking me, really, what's the area under a single point? Well, that's just 0. Oops, not C, 0. Exactly right. So this is an example where changing the bounds beforehand saves you a lot of work. You don't have to find the antiderivative, then plug back in for u. We can just jump straight to the answer once we recognize that if the bounds are the same, the integral has to be 0. Okay. So any questions on that? Okay. Well, then let's go look at number 2. Number 2, a particle is traveling in a straight line with the velocity of v of t is t minus 1 times 2t minus 4. Question 1, what is the displacement of the particle on the time interval 0 to 4? Question 2, what is the total distance traveled by this particle on the time interval 0 to 4? So, what would you guys classify this problem as? Careful, I wouldn't classify it as a derivative. Even though it's got a velocity in it, then usually velocity is associated with a derivative. But for this problem, if I have velocity and I'm trying to find distance traveled, or displacement, that's going to be an integral problem, right? And specifically, if you recall, hopefully we recall that the net change, the net change theorem, that if I integrate a velocity between 2 points, it tells me how far that, it tells me the distance that particle is displaced. In other words, the net change of that particle between time t equals a and t equals b. Okay, so we're going to be using the net change theorem for both of these. For one, we're going to integrate just v of t. For 2, we're going to integrate the absolute value of v of t, because total distance traveled, I only care about the speed, not the velocity per se. Okay, so let's go down and look at this problem then. Paste. 43, we got this. We got this, all right, part 1. So the displacement of a particle, that's traveling in a straight line, where you know the velocity is just straight up the integral over the time interval of the velocity. That gives you displacement. Displacement equals the integral from, in this case, 0 to 4 of v of t dt. And why is that the case? Well, think back to the fundamental theorem of calculus and how we know velocity is related to position. Velocity is the derivative of position. So this is what we're really finding. But then by the fundamental theorem of calculus, this is just s of 4 minus s of 0. So it tells you your final position minus your starting position. That's just how far has that changed, right? Not necessarily the total distance traveled, because I could go here and then back. Then my displacement is 0, but my total distance traveled was 2 steps, right? So that's why this theorem works. It's just the fundamental theorem of calculus in disguise. Okay, so using this, well, this is equal to the integral from 0 to 4 of t minus 1 times 2t minus 4 dt. Now, how do we want to evaluate this integral? Huh? Yeah, we definitely want to use the fundamental theorem of calculus here, but to do that, I need an antiderivative. How would I find an antiderivative of t minus 1 times 2t minus 4? It would not be a u substitution, right? This is the reason I ask. Once you learn u substitution, I think we all want to at first say, "Oh, I can maybe use a u substitution." No, just keep it simple. Try and keep things as simple as you can at all times. And the simplest thing to do here is distribute. U substitution wouldn't get you anywhere with this problem. Okay, so I want to distribute this product. Okay, so when I do that, I'm going to get, let me erase this. I'm going to get that this is the integral from 0 to 4. Well, t times 2t gives me 2t squared minus t times 4 gives me minus 4t. Minus 1 times 2t is minus 2t. And then minus 1 times minus 4 is plus 4 dt. Or after simplifying, this is the integral from 0 to 4 of 2t squared minus 6t. That's 6 times t plus 4 dt. Oh, we got to check. Okay. So what is, how would I do this integral now? Fundamental theorem pretty clearly. But again, I could break this up like we normally do. So this is, oh no, it will last. This is the integral from 0 to 4 of 2t squared dt plus the integral from 0 to 4 of minus 6t dt plus the integral from 0 to 4 of 4 dt. Okay. So then this is, well, again, pull that 2 out in front, pull this minus 6 out in front, and then pull this 4 out in front. Okay, so I get 2 times, what's the antiderivative or an antiderivative of t squared? Perfect, t cubed over 3 minus 6 times an antiderivative of t. Add 1 to the exponent, get t squared, and then divide by 2. Plus 4 times an antiderivative of 1. Well, that's just going to give me 4 times t. So plug in t equals 4, and t equals 0. Okay. So then when we do this, this is 2 times 4 cubed is 64 divided by 3 minus 6 times, well, really 6 over 2 is 3. So we'll do minus 3 times 16 plus 4 times 4. Well, that's plus 16. And then when I plug in 0, I get 0 everywhere. So after simplifying, I'll simplify this before uploading what we have so far. After simplifying this, that will be your answer for displacement. Okay. So Any questions about anything we covered today? I know Simpson's rule is a little complicated when you see it at first, but it does give you better approximations of integrals. And in fact, a very cool thing about Simpson's rule is it will obviously integrate a quadratic equation or a quadratic function exactly because we are using polynomials. But by pure chance, by pure luck, it also integrates cubic functions exactly, which is very, very, very cool. Okay, so we're going to pick up here tomorrow where we left off. Give me a few minutes to adjust the quiz and get that uploaded, and everybody will have, I'll give you until tomorrow night to complete the quiz. Okay, so if you don't have any questions, feel free to head out, and I'll see everybody tomorrow. Thank you all for being here.